Welcome to MJ School of Mining and Geology. Today, we're dealing with the most fascinating and fundamental processes in geology, how crystals form. From the tiniest building blocks of matter to the dazzling minerals we see in rocks, we're unpacking the science behind crystal growth, one unit cell at a time. Let's start at the atomic level. A crystal is not just a shiny object. It's a solid material where atoms are arranged in a highly ordered, repeating pattern. The most basic part of this pattern is called the unit cell, a tiny 3D shape that holds atoms, ions, or molecules in a very specific arrangement. Think of the unit cell like a tile on a floor. By repeating this tile in all directions, we get the entire floor pattern. In the same way, repeating unit cells create a crystal lattice, the full structure of the crystal. Crystals form through a process called crystallization, which happens when a material transitions from a fluid or dissolved state into a solid, organized structure. In geology, crystallization occurs mainly in two environments: in magmas, where minerals grow as molten rock cools, and in aqueous solutions, where minerals precipitate from water that's rich in dissolved ions. It all starts with nucleation. This is when a few atoms randomly come together in just the right arrangement to form a stable mini-crystal, the first unit cell. Once that tiny nucleus forms and survives, it becomes the seed from which the crystal grows. This process is controlled by temperature, pressure, and the availability of ions. If the conditions are just right, the crystal starts to grow. Once nucleation occurs, the unit cell repeats in 3 dimensions. Atoms or ions from the surrounding environment continue attaching to the growing faces of the crystal, always maintaining the symmetry of the unit cell. And depending on which crystal faces grow fastest, we get different crystal habits: cubic, prismatic, tabular, or even needle-like. The external shape of a crystal reflects its internal structure. For example, halite forms cubes. Its unit cell is cubic. Quartz forms hexagonal prisms, because it has a hexagonal structure. Several factors affect how crystals grow. Heavy checkmark cooling rate. Slow cooling gives large crystals, fast cooling gives small ones. Heavy checkmark chemical composition. Certain atoms build specific minerals. Heavy checkmark presence of fluids, like water, which helps ions move around. Heavy checkmark pressure. Higher pressure can lead to denser crystal structures. In nature, most crystals aren't perfect. They can show zoning, where the composition changes from the center to the edges. Inclusions, where tiny bubbles or minerals get trapped. Defects, like missing atoms or irregularities in the structure. These imperfections tell us stories about how the crystal formed and under what geological conditions. Crystals belong to different crystal systems based on their unit cell shape. Let's look at a few examples. Quartz has a hexagonal crystal system. Halite has a cubic crystal system. Pyrite has a cubic crystal system, and feldspar has a triclinic system. Each one tells us something about the environment it grew in. Understanding crystal growth is crucial in geology because white heavy checkmark, it helps us identify minerals under the microscope. White heavy checkmark, it reveals formation conditions, like temperature, pressure, and chemistry. White heavy checkmark, it allows us to reconstruct geological history using features like zoning, twinning, and inclusions. From the core of Earth to the walls of a mine, crystals are records of deep time. So, the next time you hold a piece of quartz or see a shiny crystal in a rock, remember, you're looking at something built from billions of atoms, arranged perfectly in 3D, starting with a tiny unit cell, repeated over and over through the power of nature. If you enjoyed this breakdown of how crystals form, don't forget to like, subscribe, and hit the notification bell so you don't miss any episodes from the MJ School of Mining and Geology. Drop your questions in the comments, and let me know which crystal system you find most fascinating.